All right, so it is 10 o'clock. We will get started for today. So let me get my PowerPoint up. And so today, what we're going to talk about is we're going to continue our discussion on enthalpy. There we go. So on Friday, we talked all about calorimetry, where we looked at bomb calorimetry and coffee cup calorimetry, and we were just seeing, from a reaction, could we calculate delta H? And from those, we got delta H in units of like joules per mole or kilojoules per mole. And the homework on Friday, at least the part for Friday, or the homework that was due on Sunday for the part on Friday, got some practice with that. So hopefully you are more comfortable with these problems now, as they can be quite complex. What we're going to get into today, though, is something a little simpler than coffee cup calorimetry, in that we're just going to talk about how delta H is manipulated in a equation. So just as a reminder, and sorry, my pen has been acting up all morning, so it's going to be a little hard to write here. So delta H is enthalpy. And you can kind of think of that as heat, right? So we're looking at the change of heat in a reaction. Now, delta H is an extensive property. And if you remember all the way back from the beginning of this semester, we talked about extensive versus intensive. Extensive depends on the amount of stuff that you have. So the amount of heat either absorbed or released in a chemical reaction depends on how much stuff you have in a chemical reaction. So in our example right here, if we double the amount of stuff, then our delta H value is also doubled, right? And so in our example problem that we have, right, we have A plus 1/2 B to C. The delta H of that is just some number X. So in these example problems I'm showing these slides, you can think of X as a number. It doesn't matter what number it is. Therefore, in my other reaction, so reaction 1, it's X. So in reaction 2, if I double the amount of stuff, I just double my value again. So that's all that is going on here for the first relationship. If I multiply by some factor, delta H is also multiplied. Same with division, right? If I divide all my stoichiometric coefficients by a number, delta H is also divided by that number. And our second relationship is if I reverse the reaction, that is, if I go, so here carbon is a reactant. If I just switch all the reactants and the products, right? Now carbon's a product. What happens is that the sign of delta H is switched, right? So carbon plus oxygen to CO2, that's a negative value. Well, CO2 breaking down to carbon and oxygen is a positive value. So if we look at my example again, A goes to B plus 2C. Well, if I flip the reaction, so B, for example, was a reactant or a product in my first reaction and is now a reactant, my sign of the equation flips. But if you also see here, I have decreased the amount of stuff by 1/2. So in my second reaction, my enthalpy value is negative 1/2 X. Any questions about those two relationships of delta H? If not, we will, I believe we'll move right into a problem then. Yep. So question 4. I have a reaction for you. A plus 2B goes to C plus 3D. Delta H is 155. A, B, and C, I have manipulated that problem. I want you to tell me what is the new value of delta H for each of these reactions. So try and solve that for A, B, and C. So if you're still not quite sure what's going on, I'll do A. Not much to these really. So if we look at our original problem and we look at our problem in A, all that has changed is that we have tripled the amount of stuff. A went to 3A, 2B went to 6B, so on and so forth. So we take our value, 155, right, and we multiply it by 3 to get 465 kilojoules. So 465 kilojoules. For B, so that's A, this is B right here. What's happened is that we've just flipped the equation, right? So C was a product in our original equation. Now it's a reactant. So all we need to do is flip the sign. So for B, it's negative 155 kilojoules. For C, we flip the sign and everything has been reduced by 1/2. So A went to 1/2 A, 2B went to B. So for C, it becomes negative because we reverse the products and the reactants. And we also reduce the delta H value by 1/2, which means C is negative 77.5 kilojoules. So any questions about how delta H changes when we change a chemical reaction? Can I repeat what again? All the answers? Sure. So A, we tripled, well, sorry, A, we doubled the, no, we did triple that. A, we tripled the amount of stuff. So our delta H value also triples. B, we reversed the products and the reactants. So what was a reactant is now a product and vice versa. So in B, all you do is you change the sign from positive to negative. In C, we reverse the products and reactants again. And we basically multiply them all by 1/2. So instead of A, we have 1/2 A. Instead of 2B, we have B. And when you multiply your reaction by 1/2, you also have to multiply your delta H by 1/2. So C is negative 77.5 kilojoules. All right, moving on. The next thing we're going to work on is another relationship that I didn't have an actual individual slide for. So let me just make an example here. So when doing delta H's, you can, when you combine separate equations into one equations, you also combine their delta H's. What I mean for that is if A going to B as a, let me get my pen out. If A going to B has a delta H of like 10, and then like C going to D has a delta H of 20, and I combine these two equations to say A plus C goes to B plus D, to figure out the delta H of this new equation, you just add the delta H's of the separate equations. So A to B, delta H is 10. C to D, delta H is 20. Therefore, A plus C going to B plus D is 10 plus 20, which is 30, right? So I have a reaction here, and below that, I have two separate reactions. Your goal is to manipulate these two separate reactions and try to make this reaction and tell me what the delta H is. So you're going to have to manipulate the two reactions on the bottom and combine them in such a way to make our top reaction. And I want you to tell me delta H for this process. So I'm going to give everybody a couple minutes and try to do this. This is like a puzzle. So see if we can't puzzle this out. So if you're having trouble like how to like puzzle this out, some of the things I look for is I just look at my first reactant. So this would be iron 3 oxide. And I notice that it's a reactant, right? And then I look at my equations on the bottom here. In our first equation, we have iron 3 oxide as a product. So I need to flip that. I need to have iron 3 oxide as a reactant. So what I'm going to do is I'm just going to rewrite my first mini equation to have iron 3 oxide on the right part. So Fe2O3 goes to 2Fe plus 3/2 O2. When I do that, delta H flips signs because that's what I just did. I flipped my equation. All right. So we have equation number 1. We have our Fe2O3 on the right side. We have our iron on the right side. That's good. If we look at the amounts, we're also good at that. We have 1 mole of Fe2O3, 1 mole of Fe2O3, 2 moles of iron, 2 moles of iron. So I don't need to manipulate that equation anymore. That one's good to go. If we look at equation 2, let's just look at our next reactant. We have carbon monoxide on one side of the equation, on the reactant side. And in our mini equation on the bottom, carbon monoxide's also on the left side of the arrow. That's good. The only problem, though, is that in the reaction we want to go to, there are 3 carbon monoxides. And in our equation on the bottom, there's only 1. So I need to triple the amount of carbon monoxide I have on the bottom. So let's do that. So the second equation I'm going to manipulate by multiplying everything by 3. So 3 CO plus 3/2 oxygen goes to 3 CO2. When I do that, when I multiply everything by 3, my delta H value for my second equation also gets multiplied by 3, which means it is now negative 848.1 kilojoules. Now, let's add these two equations together. So I get iron plus 3CO plus 3/2 O2. And that is making 2Fe plus 3/2 O2. Whoops, sorry, that's 3/2 O2 plus 3 CO2. Now, when you're doing chemical reactions like we talked about when we were looking at the complete ionic equation, how to go from complete to net ionic equation, if you have something that's the same on both sides of the arrow, that cancels out. They're just a spectator, and so they aren't actually doing anything using chemistry. So we have 3/2 O2 on one side, 3/2 O2 on the other side. So those cancel out. And so the equation we're left with is iron 3 oxide plus 3 carbon monoxide goes to 2 iron plus 3 carbon dioxide, which is our target equation, which means we have manipulated our equations correctly to get our target. And since delta H's are additive, we just add the two delta H's together. So we're adding 824 to negative 848. Our delta H of this reaction then equals negative 23.9 kilojoules. So that's how we can use manipulating separate equations, combine them into one equation, and calculate delta H for this one equation. Questions about that idea? Yeah, there are no questions. We will move on to our, oh, let's see if there is. You're gonna need help. I can put more practice problems up then, and your homework will also have problems like this on there. Um, yeah, it's like I said, I always think of this like a puzzle. I have two separate equations here. How do I manipulate them so that when I combine them together, I get this one equation back out? And the idea is whenever you manipulate one of these equations, whatever you do I flip the arrow? Do I multiply? Do I divide? You just have to do the same thing with delta H. If you flip the equation, the sign of delta H changes. If you multiply the equation by some number, you multiply delta H by that number. If you divide the equation by some number, you divide delta H by that number. And then finally, when I'm combining my equations back together, you just add delta H to get your final delta H. But yep, there will be a homework example with this that will let you test this on your own. I can also make more problems like this. That's no issue. All right. So we're going to continue our discussion on enthalpy now. And we're going to look at what happens with enthalpy when we create something or during a chemical reaction in general. So we need some definitions here to begin with. First, standard state. So when we're talking about standard state, it's just a definition that chemists give to have a baseline. By that, I mean, let me get my pen out again. In a chemical reaction, oh, where is it? There it is. Yeah. In a chemical reaction, you really can't measure like the amount of enthalpy. You can't measure the amount of energy. What you can measure, though, is change. So like in a chemical reaction, I can tell you how much the enthalpy changed. I can tell you how much the energy changed. But I cannot tell you the enthalpy itself, and I cannot really tell you the energy itself. So to better calculate these changes in enthalpy, all the chemists in the world have decided, okay, something has to have an enthalpy of 0. We have to say something doesn't have like a heat. And that is what standard state is. Standard state is a state in which enthalpy is 0 for that compound. That's what it is in a nutshell, and that's why we have it, because we just have to make up what is 0 so we can compare other molecules to that base state. Different conditions will tell us standard state for different types of molecules. If you're a gas, your standard state is 1 atmosphere. If you're a solid or a liquid, it's your most stable form at 1 atmosphere and some temperature, usually room temperature, 25 C. If you are in a solution, your concentration will be 1 molar. Right? And so we can calculate this value called delta H naught. What this naught is that what is the change in enthalpy if we're just looking at standard states? And we also have this delta HF of formation. That is, if I'm creating something, what is the change in formation, all right, from its constituent elements? And the elements are in their standard states, and delta HF, 0 of a pure element is always 0. So I actually got a little, I told you a little lie there. Standard state isn't when we're 0. It's in the pure element in its standard state where we say delta H is 0. So if we're looking at pure like carbon in its solid form, delta H of like pure carbon is 0. But you can have other forms of carbon in their standard state and delta H won't be 0. I know, super confusing. Probably what all I just said probably did not make much sense, but that's okay. I'll show you how to use this information and how to use it in a calculation. And hopefully by actually working with the numbers, that'll make a lot more sense than me trying to explain these topics. So what we're going to do is we're going to calculate how enthalpy changes during a chemical reaction. That is, we're going to calculate the standard enthalpy change of a reaction. So remember that not, or this 0, it's actually pronounced not, but you can think of it like an O or a 0. This just says everything we're looking at in a chemical reaction is in its standard state, right? So gases, 1 atmosphere. Solutions, 1 molar. Solids in their most stable state. And to calculate how enthalpy changes during a reaction, we do the sum of, so remember in math, this capital sigma or giant E just means add everything together that comes after this. So we're going to do the sum of the number of moles multiplied by delta H of formation of products minus sum of number of moles delta H formation reactants. Again, I'm sure that doesn't, if I say that to you, that does not make much sense. So let's see how to use this equation to see better understand what it is. All right. So in A, I'm going to do A for us. Question 6 is, I want us to write an equation for the formation of each compound from their elements in their standard state and find delta H of formation for each reaction. So first off, whenever we're dealing with delta H of formation, so delta H formation, you'll know if we're doing this type of problem by seeing this symbol. Change of enthalpy at standard state forming a new compound. That's what that variable means. Delta is change, H is heat or enthalpy, the not is standard state, F is creating something, formation. So A, we want to know what the delta H of formation is for creating NO2. How much heat is absorbed or released when we create NO2? The first thing we need to do is we need to write an equation, that a chemical equation for the creation of NO2 from its compounds and their standard states. So the compounds in their standard states will always have a delta H formation of 0. So I'll always give you a table for this problem or these problems. And you know the element is in their standard state if the energy is 0. So I need an equation where I'm making NO2. NO2 is made from nitrogen and oxygen. So I'm looking at my table for for nitrogen where delta H of formation is 0. That's N2 gas. Yes. And where oxygen is 0. That's O2 gas. So we have N2 gas plus O2 gas makes NO2. Now this needs to be balanced as well. So you can see on the left, we have 2 nitrogens, and on the right, we have 1 nitrogen. So I need to put a 1/2. Delta H of formation are the only type of reactions, well, one of the few types of reactions where you can have like a 1/2 mole. Most of the time, that does not make sense. Anything we've talked about up to this point in this class, I've always said you can't have 1/2 of a thing. Here's an exception. You can have 1/2 of a thing when we're doing delta H of formations. So that's the equation. I'm sorry that my penmanship is not great today. 1/2 N2 plus O2 makes NO2. Now we have to calculate the delta H of formation for this reaction. So our equation is you take the products first. It's products minus reactants. And it's the sum of N delta H F0 of your reactants minus sum of N delta H formation, or sorry, this is your products reactants. So let's do the products first. So we only have one product, NO2. So I don't have to do this really the sum of anything. First, N, right? So N is number of moles of NO2. Here it's 1 because there's nothing written from NO2. So this is going to be 1 multiplied by the delta H formation of NO2. We look at our table, that's 33.2. And this is going to be minus, now it's going to be the sum of our reactants. We have 2 reactants, so we are going to add stuff here. First, N2. So this was this was NO2. This is N2. So N is 1/2. So 1/2 multiplied by our delta H of formation of N2, which from our table is 0, plus, now we're going to do O2. O2, the number of moles is 1, multiplied by our delta H formation, which is 0. So these two things equal 0, so it's actually a super easy calculation. The delta H formation of NO2 is 33.2 kilojoules per mole. And for our first questions here, the answers are actually given in the table. So you don't need to do the math that I just did here. You don't actually need to do that equation. But what I would say is I'm gonna let you do practice here to try and follow what I did for NO2 and see you can do it for the other compounds. I want you to write out the full mathematical equation like I did for NO2, just to get practice of how this equation works, to wrap your mind around it. So with that, I will give everybody a few minutes to see if you can understand how this works and try to give me chemical equations and mathematical equations for the delta H formation of MgCO3, C2H4, and CH3OH. So see if you can muddle your way through that. let's try and do B here. So we have MgCO3. So that's what I'm making. It's made out of Mg, so Mg solid. It's made out of carbon, so carbon solid. And it's made out of oxygen plus an O2 gas. All right, so Mg is balanced. We have one on each side. Carbon is balanced. We have one on each side. But our oxygen are not balanced. We have O2 on the left, O3 on the right. So I need to modify that. And it's going to be 3/2. Because 3/2 multiplied by 2 is 3, right? The math I just did was 3/2 multiplied by 2 over 1 equals 6 divided by 2, which equals 3. All the way back to middle school math there. All right, so that's our equation. Let's calculate delta H of formation. Again, I'll do this again for B. Then for C and D, I'll just show you the equation because the chemical equation, because the mathematical equation is like the same over and over and over again. So it's products minus reactants. So we do our products first. So MgCO3, we have 1 mole of that multiplied by negative 1095.8, which is given from the table. And from that, we're going to subtract all our reactants. So Mg first, 1 mole of that multiplied by 0, plus carbon next, 1 multiplied by 0, plus now oxygen. So we have 3/2 moles of that multiplied by 0. So again, the answers for like what the actual delta H is, the numerical value, are just given straight in the table. But I want you to practice the math because in our next question, that is not going to be the case. So any questions about how I got B? Like any of the logic there? We're still working it out. Okay. Well, for the sake of time, I'm going to show C and D just because I need to keep moving here. So C, we're making C2H4. So we're making something that's from carbon. So I need 2 moles of that. Plus hydrogen. So natural state of hydrogen is H2 as given in the table. I couldn't really draw an arrow. So it's going to be H2. We need 2 moles of that because we are making C2H4. So carbon solid plus H2 gas will make C2H4 gas. And our last equation is CH3OH. So it's made out of carbon solid. It's made out of hydrogen, 4 hydrogens. So again, I need 2 moles of H2 plus now only one oxygen molecule. So it's 1/2 O2 gas will make CH3OH liquid. So that's how we write an equation for delta H of formation reactions. Any questions about anything I did there? Yeah, these problems, I wouldn't say they're hard. They're just, you just have to do them a few times and know what's going on. Yeah, they're all balanced. I balanced them as I went. And the mathematical thing, like I said, I'm not going to rewrite for C and D because it's the same thing as A and B. And the answers are given in the table. But in 7, there's where that mathematical equation is going to come into play. So I wanted to save our time for that. All right. So let's go to question 7. So just heads up, I realize looking at the time, we're probably not going to get the PowerPoint that I had for today. That's okay. I actually anticipated that. So the PowerPoint for today only is like the Monday PowerPoint is like super short. So we should be able to do Monday, Wednesday in one sitting. So no problems there. Okay, question 7. We are now going to use enthalpies of formations to calculate delta H of reactions. So in the last problem, I gave you a molecule and I said, come up with a chemical equation to calculate delta H of formation for me. Here, I already have the equation for you. What you need to do is use the table to calculate what delta H reaction is. So I'll do A. So remember, I'll rewrite the equation that we're using. It's the sum of, the sum of moles delta H formation products minus sum of moles delta H formation, F goes on the bottom, my bad, formation reactants. So let's do A. We have our only product here is C2H6 and we only have 1 mole. So C2H6. We have 1 mole of that multiplied by the delta H of formation, which we get from the table. 1 multiplied by negative 84.68. From that, we're going to subtract. Okay, now we have multiple reactants, so we do have to add those together. So let's start with C2H4. So C2H4, I only have 1 mole of that, so it's going to be 1 multiplied by my delta H of formation for C2H4, which is 52.4 plus, so minus there, plus my other reactant H2. H2, we only have 1 mole of that as well, multiplied by the delta H formation H2. H2 is an element in its standard state, so delta H formation of that is 0. So all I'm doing is negative 84.68 minus 52.4. That is negative 137.1 kilojoules per mole. That is the delta H reaction for question 7A. Any questions about how I did A there? And these questions were basically using the mathematical equation that we kind of skipped down in the last question. That's why I wanted you to actually like figure out how to use that equation, because I knew this question was coming up. But yeah, try to do B, C, and D now. See, you can't get any numerical value. Calculate delta H reactions for B, C, and D. And this will probably, yeah, this will definitely be the last problem that we do. If you have questions, of course, always let me know. Explain in a Barney style. Well, the idea is I tried to do things as simple as possible in many repetitions, as that's probably the easiest way to learn. Chemistry is not that complex. It's just more complex because we're using words we don't, you're learning a new language. That's what makes it complex, I think. But the actual concepts of it, once you strip away all the foreign language, are relatively straightforward. At least I hope. I think they're actually coming out with a Barney movie, if I remember right. I think I heard that like this weekend. Speaking of Barney style. The new Barney reboot movie, Barney 2.0, Barney's Back for Vengeance. Actually, I think it is supposed to be a darker version of Barney, from what I heard. Anyways, that's not chemistry. All right, time is more or less up. So what I'll do for B, I will work out B like I did for A. Then for C and D, I'm just going to give you the answers so you can check those. But I'm going to erase A, and I will I'll work out B again. So there's my pen. So products minus reactants. So our first product is H2. We have 1 mole of that multiplied by formation, which is 0. We have another product, which is CO2. So plus 1 mole of CO2, so 1. Then our value of CO2 in the table is negative 393.5. So those are our products. We're going to subtract those from our reactants. So our first reactant is carbon monoxide. So minus 1 mole of carbon monoxide, 1 times negative 110.5. And we're going to add that to our other reactant, H2O gas. Make sure you're picking the right H2O because I do have an H2O liquid in there. So plus gas H2O plus 1 mole of H2O gas, which is 1 times negative 241.8. And when I do that, I got negative 41.2 kilojoules per mole. C is negative 136.5 kilojoules per mole. D is 290.7 kilojoules per mole. These are all delta H's. So that is how we can use delta H of formation to calculate a delta H reaction. And like I said, we are out of time here. So if you do have questions about this idea, feel free to shoot me an email. I'll put up a homework that will give you more practice on this. Then on Wednesday, we will cover the PowerPoint we had for today, which really doesn't take that long. It's actually really quick. And then we'll move on. But this was our last PowerPoint on enthalpy And Wednesday, we're going to look into light. How does light work with chemistry? Yeah, that's all I have for everybody. Hope everybody has a good rest of their Monday. Do we have an exam next Monday? I think so. I have to check the schedule. I don't have these things memorized, unfortunately. I can check really quick here if you want. If it says it on the schedule, then yes, we do. Next exam is November 4th. No, it's next week, Wednesday. Not on Monday, Wednesday. Yep. So exam 3, Wednesday. And I will see everybody later. Have a great one.